All right. Stop talking, please. So, Joe asked about 8 and 9 from this homework 4.5 here. So this is all going to be kind of done on your calculator. So the first thing I would do is I'm going to press the y equals button and then clear out anything I might have had in there from before and type in the equation exactly as it appears on my sheet of paper, which if you look, you can see that I've already done that. Yes, sir.
Okay, quick question about the calculator.
Uh-huh.
My brother actually had to take his calculator back.
Okay.
That's the one that I was using.
Okay. Okay.
So how do I get the
So if you go to, you're talking about the thing that I'm running right now?
Yeah.
If you go to Power School, I have under the resources tab, there's a link.
Oh, thank you.
Yep.
Wait, how do we, oh wait.
So the X button is right next to the alpha. You don't have to press alpha first. If you look right next to it to the right is a button for a variable.
No, it's like still square.
You can do it the same way you did the cube.
So my I did X and then I did like the mini carry for a second and it's not going back to my plus. It like adds it to the
So just press to the right and it'll return it back to the main line again. That's okay. You're welcome. Again, it's your first time using these things, so it's fine. Joe, you're good to hear? Okay. All right. So once we've, stop talking, please. Once we have our equation typed in, we're going to press the zoom button on the home row there and pick zoom standard, Z standard, that's option number 6. And that'll graph us our function. So if I look at this, it looks like maybe there's a maximum like right there and a minimum right there, but it's kind of hard to see, right? So what I'm going to do is I'm going to readjust my window so maybe it's a little easier to see what's going on. So if I look at this, the area that it seems like that's of interest to me is like just this little section right here. You guys agree with that?
Yeah.
Well, if it looks different, either your window is different or you typed in the equation incorrectly. Just press the y equals again.
Wait, what? Mine looks like a straight line.
Okay.
Oh, it's actually 30.
Oh, is there?
You do it the same way you did the squared with the caret thing.
And then after I go back, do I have to go back to zoom?
You should just hit, that's fine, you can do it that way. So, I'm going to, it looks like on the X, what I care about is between 0 and 5, and then on the Y, maybe between 1 and -1. Everybody kind of agree with that, looking at this picture that I have? So if the part that I care about is here, so that's like 0 to -5, and then -1 to +1. So I'm going to go press the window button and just readjust things so I can see a little bit better what's going on. And the numbers I chose don't matter too much. I just wanted something that's going to be a little bit, like a little bit closer. Yeah, what's up, bud? Do you need to go to IT to get it installed or whatever?
It's just with this browse ROM image, like,
Well, you don't have that on your calculator.
I could just skip without it today and buy one.
Okay, now what do I do? Why won't trace?
I don't know what's going on. Yeah, part of the issue here is that everybody is trying to talk at the same time I'm talking about things other than what's actually going on, so it's making it difficult for me to field questions and answer questions and narrate through exactly what's going on. So, starting from the beginning, we went to the y equals button. We type this in exactly as it looks on your sheet of paper. To get the exponents, you're going to use that caret button right above the division sign. You're going to need to type in your x's using that button on one button to the right of the alpha key. That's the green one on my calculator. But it needs to look identical to what I've typed in here, which should look identical to what's on your sheet of paper, right? Notice the exponents look like exponents and everything. Everybody's okay? Okay. Next thing we do is we're going to press the zoom button and pick zoom standard. Just press the zoom button. No, just press the zoom button.
I did, but then it says zoom out.
You pressed one button.
Oh.
You just left or righted it or something there.
Okay.
It's okay. And we should have a graph that looks something like this. Okay? Now the issue with this is it's hard to see the maxima or minima if there are any going on here, right? It potentially looks like maybe there's a maximum here and maybe there's a minimum here, but it's kind of too far away for us to tell what's going on. So I'm going to resize my window so I can get a closer view of that area that I'm interested in. So if I think about it, it seems like this is the only part of the graph that I really care about, is like that little rectangle there. Is that okay? Yeah, where the thing is squiggled. So if I were to describe that rectangle, it looks like it starts at maybe -5 on the x and goes to 0. and then it starts at -1 on the y and maybe goes up to +1. Would be like the way to describe that rectangle, right? It's 5 this way from -5 to 0, and then 2 this way from -1 to +1.
So you're getting the -5 for like the.
On the x-axis,
Okay.
yeah, yep. So that's just, and again, those numbers don't really matter too much. You just want a better picture than what you're looking at. So if you said like -6 to 0, would be fine. If you did -2 to +2 instead of -1 to +1 on the y's, that would be fine. You just want to get a little bit better picture than what you're looking at. So to resize your window manually, we're going to press the window button. And then I'm going to do, for x min, I'm going to do -5, and x max 0. And then y min -1, and y max +1. Everything else is just going to stay whatever it was before. An easy way to remember this is the minimum should always be smaller than the maximum. So if you forget which number should go where, just remember the smaller number needs to be the minimum and the bigger number needs to be the maximum. And once you've done that, you can press the graph button on the far right on that top row. And you should get a much better looking picture, where it's quite a bit easier to see your maxima and minima. Did that work for you there, Hallie?
Yeah.
Okay. Okay. So I see one maxima here and one minima here. Yes.
Can you go back to the window page and look at this?
You guys can turn the light out if you have trouble seeing the screen.
Yeah.
Just as for everybody's reference, if you ever have trouble seeing and the lights are in your way, like, you don't have to ask, just stand up and turn them out. They're usually on first thing in the morning because it's so dark out, but as the day gets lighter, they become less necessary, especially with the projector going. It's probably a bit easier to see the screen now, right? Okay, you got it?
Yeah.
Okay. So let's find this maxima first. Sound good? Okay, so I'm going to press, so this is the picture I would probably sketch here, by the way, for part A. And then we labeled this as the maxima and this is the minima. They're both locals. We can tell they're locals because we definitely have stuff that's higher than the maxima on this end and lower than the minima on that end, right? Okay, and now let's use the graphing calculator to find the coordinates and round those to 3 decimal places. So to find the maximum, we're going to press second and then the trace button. From that menu, I'm going to pick the maximum command. And now the calculator is going to ask me 3 questions. Left bound, and then right bound, and then guess. Right now, if you look at the bottom of the screen, it's asking me for a left bound. So all I'm going to do is move my cursor, you see the cursor flashing on the screen, somewhere left of where I think that maximum is. Anywhere on the left side of it is fine. So this spot I'm at looks good to me. I'll just press enter here. You'll notice now the question has changed to be asking for a right bound. So now I'll move my cursor so it's on the right side of that maximum. Almost anywhere to the right of it will be fine. That looks good. And then I'll press enter again. And now the question says guess. Any guess is fine as long as it's in between the 2 bounds. So just right where it's at is fine. So I press enter again. And it now has spit out my maximum. So rounded to 3 decimal places, I would write -2.577, comma, 0.385. That okay? To find the minimum, I'll now press second and the trace button, and this time pick the minimum option. And the calculator is going to ask me the same 3 questions: left bound, right bound, and guess. So this time I'm going to move my cursor so it's somewhere left of the minimum. That looks good. And press enter. Now I need a right bound, so I'll move it somewhere to the right of that minimum. And then press enter. That looks good. And then I guess it doesn't matter. I'm just going to guess right where I'm at. And here comes my minimum, which is rounded to 3 decimal places, negative 1.423, comma, negative 0.385. Okay with that? Negative 0.385. So again, from a mathematics standpoint, the only thing that we really had to be able to do was to be able to visually identify where the maximum or minimum were on our graph. And the rest of it, the calculator handled. Now we had to remember like where the commands were on my calculator and what kind of inputs I need to give to the calculator and how to type things in and where the buttons were at and all that kind of stuff. But in terms of mathematics required for us, it was really just some visual skills, right? Can I look at a graph and find the stuff that I'm interested in? Which hopefully isn't too bad once you've got the calculator part handled. Okay? Joe, does that feel a bit better? I'm gonna skip doing 9 because it's really the same thing. Obviously, if you do 9 and you want me to look at what you did or want to check things with me, I'm happy to do that later. But it should work almost exactly the same way. Hallie?
This is just like, on like 4, the first 2 questions, are those like the same way that we just did?
Homework 4.
I think it is.
Yes.
Okay, alright, I'm done. Thank you.
You're welcome. Other questions from homeworks? Bianca?
So this is like Hallie's question.
Sure.
So I think I did that one wrong. Like, we had to use our calculator with the 1 and 2 equation for each graph? Or did we just have to look at the graph?
Oh, for 1 and 2, that's how you would get. So the directions say graph it on the calculator, find the coordinates of the extrema, and then indicate if it was a max, min, local, or global. So you could have done that third part just by looking at the picture,
Okay.
but to get the actual coordinates, you would have needed to do the max and min part.
Okay.
Yes, sir.
Can we do number 7 on 4.5?
Mm-hmm. Okay. So this one, I did a bad job in giving you guys a clearer idea of what was going on, which is my fault. So notice at the end it says assume there are arrows at the ends of each graph. That was the last piece of the instructions. But when we get to number 7, it's not entirely clear what it is the arrows would be doing, right? From what I've given you. I mean, you might assume, oh, they're just going to go straight, or oh, it's going to go up, oh, it's going to go down. It's not entirely clear what would be happening there. Well, in fact, none of those are what I actually intended for you guys to interpret that as. My intention was you to interpret it just keeps on going, doing that same thing that it's been doing for till the end. Now, unfair of me to expect you to come up with that given the instructions that I gave you. That was probably not a fair assumption of mine. And obviously on the homework, like, if you didn't interpret it that way, don't worry. Like, I realize it was a bad question or badly constructed question on my part. But let's talk about what you would do assuming that you did interpret it the way that I've just kind of described that I would have wanted you to. So we ask you to do a whole bunch of things here. So one of them was the domain and range. So let's start there. The domain is talking about the x coordinates that are used by the function. Now, if both of these ends are going to kind of do this forever and just keep on like doing their squiggles, the farthest left point is negative infinity, and the farthest right point is at positive infinity. So that's my domain. Okay with that? If I do the range, though, the lowest point would be, any of these at like the bottom of these troughs, the valleys here. And the y-coordinate there looks like to be about -1 to me. And the high point would be like at any one of these hills, the top of any one of these hills. And the y-coordinate there to me looks like +1. So my range would be -1 to +1. And because it looks like there is a point that has the y-coordinate -1, I would use a bracket. And there is a point that has the y-coordinate +1, I would use a bracket. Okay with that? Now, for the next, the positive, negative, 0 parts, the issue here becomes, well, if this goes on forever, like this a positive part, but so would this and this and this and this and this, and there's like infinitely many of them, right? Well, that's not very plausible for me to write down. So what would I do in that sort of a situation? Well, there is a notation that we could use to do this, so I'm not going to worry about that with you guys in this kind of a class. That's beyond the scope of what I'd expect. So we're just going to kind of describe what's going on here in words. So we're going to give one of these positive intervals and say, and then we get another one every whatever number of units. That sound okay? So let's use this one as our one that we're going to describe. Okay? So if I look at this, it looks like we go from 0 to, well, when I do the bottom back up, I go to a little bit past 6. So this spot here is probably like a little bit past 3. I'm going to call it 3.1. Now, if you estimate it as something else, that's okay. Like, again, I didn't give you points, so you're stuck making your own estimates, but I'm just kind of talking through the estimate that I would make. So our positive interval would be from 0, 0 here, to 3.10 there. No 6, because this part is negative, right? Because you're below. Okay, so that's a positive part. And then I would say, and every, let's say 6.2 units before and after it. So like if I pick this up and move it 6.2 units, I would get another positive interval, whether I moved it forwards or backwards. Does that make sense? Okay. Is that okay with everybody? Yep. Again, this was a poorly constructed homework question on my part because I wasn't clear enough at all what you'd expect the ends of the arrows to do. And then even if you did interpret it the way I did, to do this kind of in-betweeny wordy description is maybe not realistic, or a realistic expectation on my part. But we should talk about what to do. even if this isn't what you did do, right? Okay, the negative parts, well, again, there's infinitely many of those, right? So can't list them all. Let's do the same thing we did before. Describe where one of them is and then say, okay, and then every whatever before and after that. So for the sake of argument here, let's use this one. So that one goes from negative 3.1 back to 0. And then every 6.2 units before and after. Okay with that? And then my zeros, well, again, I have like infinitely many places where that crosses, right? Now the catch here is that it crosses at a singleton point. So I'm still going to use like the set builder notation here. So I'm going to say we have the set of x's such that, now one of those zeros is here at the origin. At x equals 0. And then every 3.1 units before and after it. Right, because here's a 0 at 3.1, here's another 0 at 6.2, 9.3, etc., etc., etc. Now, not terribly realistic for me to have expected you guys to come up with that, especially given the lack of clarity I gave you about what's going on with the ends of the graph. And this is certainly beyond the scope of something I'll be able to do on a test. I think the previous two problems are certainly reasonable test questions in terms of a level of difficulty. I think this is probably beyond what I would expect you to be able to do on a test or quiz setting. Push this up, so we have increasing and decreasing and constant still. So the increase, I'm just going to find one of them and then describe, like, do it the same way we did before. So this looks like an increasing section where it goes from the bottom of a hill back to the top, or the bottom of the valley to the top of a hill. So if this is halfway between 0 and 3.1, that would mean this would be like 1.55. Because that's halfway between 0 and 3.1. So we'll go from negative 1.5, positive 1.55, and then every minutes before and after. Okay with that? And we'll section. If that's 1.55, this is 3.1, this would be like 415. So we'll go from 1.55 to 415. And then every 6.2 units before and after. And you'll notice that there are no flat sections of this graph, so there's no constant parts. And the last thing I'd ask you guys to do was the end behaviors. So which direction are the arrows at the end of this graph pointing? If they're doing this, there's some times where it's pointing up, but there's other times where it'd be kind of pointing down, right? Is it clear what's going on with the end behavior? No. In fact, this has no end behavior. This type of graph is called an oscillating graph. You'll see this again next year if you take trig and pre-calc. You'll deal with a lot of oscillating graphs in that course. But this has no end behavior because the arrows are not doing anything or doing the same thing all the time, right? Sometimes they'd be pointing up, sometimes they'd be pointing down. They're not pointing to a specific value even. They're just kind of bouncing around. So this would have knowing behavior. Again, rather tricky thing that happens there. Maybe not super obvious, because I don't think we saw an example in the homework where that happened, but like I said before, this is beyond the scope of something I would expect you to be able to do on a test. Now, I think that's fine in the homework, because it just gives us an opportunity to talk about some of these things here in class in like a low stake setting, but not something that I would feel like would be fair for me to expect you guys to reproduce. Okay with that? Jack, you happy?
Yeah.
Okay.
It was a little confusing.
Yeah, no, it was poorly constructed question on my part. So this probably should have been one where I just made finitely long and put no arrows at the end of it. And that would have been much more realistic to deal with. But, oh well, gave us something interesting to talk about, right?
Yeah.
Sure. Allie.
For the problem about that one,
Yeah.
can you just do the domain?
Sure.
That's all.
Yep. So the reason I know that is because I have an arrow that points down and left, and I have an arrow that points up. And since they're connected in between, my x's go from negative infinity to positive infinity. That's the domain. And then my range goes from negative infinity to positive, or my y's go from negative infinity to positive infinity. So that's my range. Is that okay? Okay. Yep. So that's usually the easiest scenarios when you have a connected graph with one arrow up, pointing up and one arrow pointing down. Right away, the domain and range are both got to be negative infinity, positive, which is a nice little shortcut when you see that. Does that help? Okay. Last call on questions before we move on. Okie doke. So today, we're going to talk about transformations of functions. And this is something you've already kind of done in your geometry class. So what I want you to do is take a moment here and step into your time machine and go back to your geometry class last year, where you talked about transformations. In your geometry class last year, you would have identified there are 4 types of transformations. Does anybody remember one of those 4? 2 of them start with the letter R. What? Somebody said something that started with an R, at least. Radical is not one of them, but I appreciate you giving it a shot. What? Radius is not one of them, but I appreciate you giving it a shot. Reflection is one of them. Yep. Okay. That's okay. This is not, we're just kind of remembering some things from it. We're not going to really, rotation is the other R one. Yep. Now there's 2. They don't start with the letter R. One of them starts with a T and the other one starts with a D. Well, transformation is what we're talking about. These are types of transformations. What? Tilt? No, that's kind of like that would be kind of like a rotation, I suppose. So the T one is translation. And the last one starts with a D. You would have done this when you talked about similar figures, I think, is when this comes up. It is called a dilation. I think that's a whole section or 2 in your geometry textbook. Okay, So when we talk about reflections, at least algebraically in this class, we're only talking about two different types. So you can reflect across the x-axis, or we can talk about a reflection across the y-axis. Any straight line, but that's beyond the scope of this class. So when we talk about reflections here, we're just talking about one of those two. In high school algebra, we're never going to talk about the rotation of a function. We don't have the mathematical tools to really do that effectively, so we're not going to even consider those situations, so you don't have to worry about that. With a translation, there's two types that we're going to worry about. You can shift left or right, or you can shift up and down. And dilations, I think in geometry you guys always did like a symmetric dilation, where you dilated the same amount vertically, horizontally. That need not be the case, although it's perfectly fine if it is. We're going to talk about, in this course though, you're going to have horizontal dilation, where you just kind of stretch or shrink horizontally, and then vertical also. So in your geometry class, if you're doing a reflection, let's say that this little triangle in red is like your pre-image. If you reflect across the x-axis, the resulting image would look something like that, right? Where the orientation changed and the location changed, but the dimensions of the figure stayed the same, the relative size and shape of it. If you reflect across the y-axis, you'd have something like this, where again, the location changed. This time the orientation stayed the same. And the dimensions, obviously, the shape of the figure stayed the same. Everybody kind of remember that? With a translation, again, if this was our figure, you could translate it, say, to the right, and you'd have something like this. Or you could translate it, and maybe you have something like this. Again, the location has changed, but the orientation and the shape of the figure stays the same. And then the last situation with the dilation, let's say that we have, there's our image. So if we dilate this thing vertically, it might look like this, where we've taken it, like stretched it out vertically. Or if we did a horizontal dilation, it might look like this, where this time it looks like we stretched it horizontally. And then you could certainly do both at the same time, like you've done in your geometry class last year. Does that help jog our memory a little bit about what these things look like? I'm really just needing this as a visual reminder of kind of what these things kind of look like. Okay? So that's the end of the geometry part, right? So that hopefully wasn't too bad for all of you geometry haters out there. So the thing to remember here, in geometry, when we did this, we usually did these transformations on like a figure, like a triangle, right? Now, if I think about it, really a geometric figure is just like a set of points, right? And in the case of a triangle, really you can simplify it down to like a set of 3 key points. Really, if you just have the 3 vertices, you can draw the triangle afterwards, right? Now let's think about this in terms of algebra, where we talk about functions. A function is really just a set of points, right? Now, there's some other criteria it has to meet, but in essence, it's still just a set of points, right? So we should be able to do these transformations on a function also. Now, for the most part, when we talk about a function, we're going to need more than just a couple key points to describe it. For a lot of these functions, we need infinitely many points to really describe the function. So the notation we're going to use is going to be a little bit different than the notation we would have used in a geometry class. And the vocabulary will be a little bit different. But the idea is going to be kind of the same. So in geometry, we had, and we did some transformation to it. I think that was the vocabulary you guys use. We have what we call a parent function. We do some transformation to it. And we call the result just the transformation, or the transformed function even. So in your geometry class, the way you described that transformation was you had a set of xy's that represented the points in your preimage, them to some transformed version of those points that you called your image. So you took the x coordinates and you like multiplied them by something or added something to them, and the same thing with the y coordinates. Now, in your algebra class, what we're going to do, if we have some parent function that we call f of x, it's acting like our preimage, we can generate a transformed function in this way. Now this right here is important. Like important to the extent that at some point you're probably going to want to have this memorized. So most of this course, yes, sir.
It says equals AF. What's the bottom number of that?
It's the letter B.
Oh, okay.
This course really turns into like a survey of functions. So the type of function that we study, the f of x in this case, will change with each chapter. But what the transformation is doing kind of stays the same throughout. So what we're about to see here is going to be true for the entire year and really the entirety of your mathematics career when it talks about, or when we talk about a transformation of functions. So it'll get to the point where you can look at the equation for something and be able to tell already, like, okay, what does the graph kind of look like? What are some important features about it? And you'll be able to really get a lot of information just by looking at the equation. Yes? That's the letter F. That's an H. That's the lowercase letter h. Yep, a times f of 1 over b times x minus h plus k.
And is this supposed to be two parentheses there?
Yes, because there was 2 parentheses opened, so we need 2 parentheses closing. Right? And these are all perfectly reasonable questions. If you can't read what I've written, like the symbols matter, right? And if you can't read it, you can ask. Don't feel bad about doing that. That's the right thing to do. While at times I'll be frustrated because my penmanship is illegible. And it's like, I can't, all right. But these are reasonable things for you to ask, so don't feel bad and don't feel discouraged if I look frustrated. I'm not frustrated at you. I'm frustrated at my own illegible penmanship. Okay? Okay. So these values, these A, B, H, and K, all correspond to a type of transformation. So let's start with A. If A is negative, then we have a reflection across the x-axis. If A is positive, there is no reflection in the x-axis. So the A is in charge of one type of reflection, right? Now the A actually has a second function. So if the magnitude of A is greater than 1, it causes a vertical stretch. And if the magnitude of A is less than, it's going to cause a vertical shrink. And if it's equal to exactly 1, we're going to have no vertical. Similarly, the B is in charge of two things. If the B is negative, we have a reflection across the y-axis. And if the B is positive, we have no reflection across the y-axis. If the magnitude of B is bigger than 1, we have a horizontal stretch by a factor of B. And if the magnitude of B is less than 1, we have a horizontal shrink. And if the magnitude of B is exactly 1, we have no horizontal. The H is in charge of just one thing. So if the H is positive, we translate to the right H units. Translate to the left H units. And if the H is equal to 0, there's no horizontal translation. And lastly, the K is in charge of just one thing, K units. If it's negative, we translate translation. Yes, sir.
You go back up. Yeah, that's good.
Yep. Now, what's nice about this set of criteria is that this does not change. So throughout the entirety of this course, this set of criteria remains the same. It'll be the same set of criteria you see next year in your math class, and the year after that, and so on and so forth, until you run out of math classes to take. So that's very nice, right? Although this is a long list of things, the fact that it's always the same list and these are always doing the same thing makes life considerably nicer. Yes. Because we're concerned about the sign of h and k, not the magnitude of h and k. So if you look at the function here, notice that the you're doing is multiplication. So when you multiply by something that's bigger than 1, it gets bigger. But if you multiply by something smaller than 1, it gets smaller, right? As opposed to adding and subtracting, where if you add something bigger than 1 and smaller than 1, well, it still gets, as long as you're adding a positive thing, it gets bigger. Does that make sense? Okay. So it has to do with the fact that the a and b are multiplying and the h and k are adding and subtracting. Okay? All right. Okay. So let's say we're asked to describe in words the transformation to f of x when g of x is equal to negative 2 times f of x plus 3 plus 5. So the first thing that I'm going to want to do, my g of x, so that it's in this form. Everybody's okay with that? Remember this form from just a moment ago? Once I have my g of x in this form, I should be easily able to identify the values for a, b, h, and k. And then use the list of criteria we just established to make that description. Okay. So negative 2f. And now you'll notice that if I look for a 1 over b, there's nothing in front of my x, right? But what number is really there that we just don't write down? 1. Now, I can write that as the fraction also, 1 over. Everybody's okay there? Next observation I make is that I have a plus 3, but the form has a minus h. How can I rewrite an addition problem as a subtraction problem? Well, minus a negative, right? So minus negative. Everybody's okay with that? And then nothing, just plus 5 at the end. So there was no issue there. Okay, so is everybody okay with that? Okay. So now I'm going to use criteria to describe what's going on here. Since my a is negative 2, I know that that's a negative value. So I have my reflection across the x-axis. Everybody's okay with that? My magnitude of a is positive 2. Since that's greater than 1, I know I have a vertical stretch. And since the magnitude of B is equal to 1, we have no horizontal dilation. Since my H value is negative, that tells me we're going to go left 3 units. And because my K value is positive, that tells us we're going to go up 5 units. So that's my description in words. And I got that just by looking at the equation, identifying the values for A, B, H, and K, and then using that list of criteria to identify what those 4 values are doing. Yes, Bianca?
So basically the list you gave us is like for each variable. So like, you're like, well, I'm just like visualizing like, for A, you have to write out like which one is it, like the less than 0, more than 0, and like I just don't know where you got it from, like all the side values.
Okay. So
Okay, so it's like just different sections, you know, like choose one for each one.
well, in the case of the A's and B's, there's 2 things to consider. You have to consider the sign, whether it's positive or negative, and then the magnitude, the relative size of that value. Right? That's what you're asking, though?
Yeah, that's what I was asking.
Okay.
I thought it was just like a big list to give us.
I mean, it kind of is.
Well, like, yeah, but like I just didn't know what it was like those for.
Yeah, whatever way you want to organize it is perfectly reasonable, and what you're describing is a nice way of kind of visually looking at that. So far, so good? So again, from a mathematics standpoint, we haven't had to calculate anything, right? We've identified some forms. From that form, we've been able to identify values. And then using those values, we've been able to like identify the type of transformation based on the value, right? Okay. Okay. Let's say that we're given that the graph of f of x is this thing that I've just written down in red. And we ask you to graph then the transformation g of x equals negative f of x plus 3 plus 5. Notice that this is the same function that we just did in the previous example. So right away, because it's the exact same thing, I can write down the values for A, B, H, and K because I figured them out in the previous example. Is everybody okay with that? What I'm going to use that now is this transformation map. Oops. That we would have used in geometry. A, B, H, and K using the ones from my list. Everybody's okay here? So all I did was I filled in the value for A, the value for B, the value for H, value K for K. Right? So just filled some stuff into a formula. And now all I'm going to do is I'm going to apply this formula to each of the 3 points in my graph for f of x. So with a little bit of mental math, if you have to do that on your calculator, that's perfectly fine, no big deal. So if that's my graph for f of x,
I'm a little.
okay, when you say all of these numbers, can you be a little bit more specific for me? I'd be happy to answer this question.
These last, like the x, y, I don't understand. So
You talking about these three values?
yeah, I know that the points in the triangle, but how are you getting the numbers?
How
Does
did,
that make sense?
so this was, all of this information was given to me as the example problem,
Yeah.
okay?
Okay,
So like, I think
So
what
the
you're
eight-
saying is like for 1, 0, you have 1 through 3, and then you have -2.
Okay, so what I've done is I've taken my value for x and filled it into x into my formula.
Okay.
And then I took my value for y and filled it into the value for y into my formula.
Okay, I see a little. Okay.
Okay?
I was just a little.
Nope, that's okay. Again, if you don't understand what's going on, you do the right thing in stopping and asking. Yes, sir.
Okay, so the a equals -2, b equals 1. That comes with the example, so that would all.
No, this is, we noted that this was the same example problem as this one.
Okay.
So I just copied down that work from the previous example.
Okay.
So I would have used on a fresh problem, but because this was like a continuation of the previous one, I just copied down those values from the previous
Let me get
problem.
another example of that later on.
Sure. No, that's okay. I appreciate you guys stopping and asking for things. This is perfectly fine. This is what I want you to do. If you're not sure what's going on, like stopping and asking is exactly what you should do. So when I plot those 3 points, this is what I get. If you compare this blue V to the red V, what do you notice? Well, it's been flipped upside down. That's the reflection across the x-axis. The blue V looks taller than the red V. That's the vertical stretch. The location has changed. It looks like it's been moved to the left and then up. That's the translation. In fact, the description that we made in the previous example exactly describes the difference from the red triangle to the blue, or the red V to the blue V, right? Did you guys see that visually? That if you look at the previous example, the description that we gave in words matches exactly what you're seeing here. Because this was the exact same example problem, right? Everybody's okay with that?
I think I got it now.
That's exciting.
Yeah, I got it.
It's exciting when that happens. This is probably like the trickiest, maybe I don't want to say tricky, like the most involved thing that we've done here, right? This actually involves a little bit of computation
So the
and has some very important, like big ideas all put together.
The one above x, y, the first x, y, you're just writing like
The points from the original graph.
equation, and then you literally just plug in.
Plug the x's and y's into the spots into that map,
Okay.
and evaluated them.
And then the b is in the original, like our equation of bx plus h.
Since the b was 1, a
It's left
1x,
x.
but I don't have to write 1x,
Okay.
right?
And then h is 3, and that's it. Okay, I got it.
Okay. All right. So, Stefan, you want an example of like pulling out the values for A, B, H, and K, right? So let's do that. Okay. So this will be a pretty pared down example because all we're going to ask to do is to identify these values for A, B, H, and K, since that was the part that it seemed like you specifically wanted some more practice with.
Yeah.
Okay. So again, the first thing I want to do is I want to remember this form. And my goal is now going to be to rewrite the function in my example problem so that it's in this form. Okay? So if I look to start, the negative 1/2, well, hopefully that's easy to see.
Yeah.
Okay? And I have my f, and now 1 over b. So how can I rewrite 2 as a fraction with a 1 in the numerator? Well, 2 over 1 has a 1 in the denominator. That's okay. You're thinking. That's good. You want to do 1 over its reciprocal. Right? What do you do when you make a reciprocal? You flip the fraction, right? What happens if you flip the fraction twice? You get back whatever you started with. So what I'm doing is 1 over 1/2 is like flipping 2 twice, right? So if you flip 2 the first time, you get 1/2, and you flip it again, you get back to 2. That's all we're doing, all we've done here. It's just like a really goofy looking way to write the number 2. If you tried typing this into your calculator, it's going to just give you the number 2. Just, so in this case, the b is 1/2. Exactly right. So if I did 1 over 1/2, I get 2. Right? Still just the number 2. So I haven't changed anything other than the way it looks. Okay? And then we have a plus sign here, but we're supposed to have a minus sign. So the trick we use there is we're going to write minus a negative. Which tells me then the h is -6. And then again, I have a plus here, but I'm supposed to have a plus, so I'll write this as plus a negative. So there's my values for A, H, and K, or A, B, H, and K, excuse me. Does that feel better, Stefan?
Yeah.
Okay. You're welcome. So, for this weekend, I have homework 5 that I've posted on transformations. I have the chapter 1 review that I've posted. I have a key for the review, so you can check your work on that. The test, or well, next time we'll take questions from stuff. We'll talk about the test format. we'll start the next chapter a little bit. And then next week, in our first class next week, I think that's Tuesday, we'll take the chapter 1 test. Okay? Fair enough?
Thank you.
All right.
Thank you.
Yeah, you're welcome, guys.